Welcome back to Dave Does Math from Home. This is part 2 of our video on section 13.2, vectors in space. We're kind of done with the vectors. Now we're mostly just going to talk about space. Uh, there's a couple, we're going to get into multidimensional functions, functions that represent surfaces in space. We're going to get into that much more in the next chapter, chapter 15-ish. But we're going to sort of build up to it. This is part of the build up. We're going to talk about some very basic functions and what those look like in space. We're going to try to connect these two functions that we know. So in 2 space being the xy plane, it's two-dimensional space. I'm going to call that 2 space a lot. So that's 2 space. This is 3 space. Theoretically, you could have 4, 5, 6 space. That's where you get hypercubes and stuff. But mostly, we're just going to deal with 3 space and compare that to what things look like in 2 space. In 2 space, a function like y equals 6 is a straight line at 6. In 3 space, I'm going to see if I can draw one of these numbers here. So this will be x, this will be z going up, and this will be y going sort of out. In 3 space like this, the function y equals 6 is going to give you a plane. So y equals 6 is any combination of z and x you can get where y is 6, which gives you this entirely flat plane at y equals 6. If you wanted to look at a different one, like z equals 4, that's this plane right here. So any point that is exactly 4 units above the xy plane is the z equals 4 plane. If you wanted to do z equals like -12, that would be a similarly flat plane over here. X, you can probably imagine, x equals 3 is going to be a vertical plane this way somewhere. So that's the first thing. Things that used to be lines are now planes. You just fix a point somewhere, you get a plane. X, Y, Z. So here's another attempt at having an xy plane here and z going up above it. If you want something like you can get planes that sort of look like triangles in the first octant pretty easily by looking at the plane that goes through 3, 0, 0, 0, 2, 0, and 0, 0, 5. So if you sort of just connect 3 dots, you'll always get a flat plane. And in this case, you get a plane that's sort of slanting downwards. I did just say the word octant. In the xy plane, we have 4 quadrants. 1, 2, 3. That's not how we do the 3. 3 and 4. These are our 4 quadrants in 2 space. In 3 space, you end up with 8 of them. There are 8 octants. And I have no idea which one is which. In 2 space, I know the order. It goes counterclockwise. It's very easy to count them. In 3 space, the idea of counterclockwise kind of falls out the window. Like what? I don't know where you go. I know what the first one is. The first quadrant is the one where x and y are both positive. And the first octant is the same. The first octant is the octant where x and y and z are all positive. So that's what we have here. This is the first octant. So like if we went back this way, x would go negative. If we went back that way, y would go negative. And if we went down, z would go negative. and any one of those could be the second octant. I honestly have no idea. But I know that the first octant is this one, where x and y and z are all positive. So that's a very brief introduction to flat surfaces, and we'll get more into that later. Right now, I just want to focus on visualizing these things. So let's talk about some very basic curved surfaces. Let's start with everyone's favorite two-dimensional shape. I'm not going to call this a function because technically it's not a function because it doesn't pass the vertical line test. But it is the unit circle. X squared plus y squared equals 1 is the unit circle. Something that we probably should have talked about in pre-calculus but didn't is how you can change the circles around. If you want to move this, we did talk a little bit about shifting functions from left to right. If you want to move something 3 units to the right, you have to subtract 3 from the inside of the function. Turns out, if you're dealing directly with x's and y's in an implicit way, all of your operations end up being sort of like backwards like that. So this is, let's make it 25. This is now, it's still a circle, because it's still x squared plus y squared equals some number. But it's been moved 3 right, 2 down, and the radius is 5. 1, 2, 3, 1, 2. So it'll probably go back here to -2 if the radius is 5, and we'll go up to +3 over there. Okay. So I have a big radius 5 circle centered on the point 3, -2. And that's what I get from this in 2 space. Some of you may be anticipating what happens when I do things in 3 space. X squared plus y squared plus z squared equals 1. This is no longer the unit circle. This is the unit sphere. And messing with the unit sphere works exactly the same way as messing with circles do. If you want to move the center in any of these directions, you can subtract that number from inside the squaredness. So you could do something like x minus 1. This will move it 1 unit to the right. Plus y minus 5. This will move it 5 units up. Let's not mess with z. Yeah, we can not mess with z. So this will leave it sort of centered on the z-axis still. And then we can say whatever number we want this to equal, like if we want the radius to be 3, we'll say it equals 9. Now the radius is 3. So this will get you a sphere. I'm going to try to sketch this. I think it's probably not going to work, but I will attempt. This is x, and this is y, and this is z. We're going to have something that is 1, 2, 3, 4, 5. So the center will be here, and it's not going to go up or down on the z-axis at all. It will be on the xy plane because nothing is being added and subtracted here. We could move it up or down if we wanted. Like if you wanted to slide it up the z-axis 4 units, you would do a z minus 4 here, and then it would move up. And if we wanted to have radius 3, imagine that that's a sphere. I can't draw in 3D at all. This is a mess. But the analytics of it, check out. Works exactly the same as it does in 2 space. You can move the center around however you want by subtracting those numbers from inside the squaredness of each variable. You can set the radius of it whatever you want by making this the radius squared. Essentially, what you get is x minus a squared plus y minus b squared plus z minus c squared equals r squared is a sphere centered at A, B, C with radius r. So I think the last thing I need to mention about spheres here is that this gives you a sphere in the same way that x squared plus y squared equals r squared gives you a circle. And that means that the sphere is all of the points that are exactly that distance away. So spheres are, think of spheres as like balloons. There's a very thin shell of a shape, and you're only dealing with the outside of that shape. You're not looking at the insides at all. If you want to talk geometrically about a sphere and everything inside the sphere, the geometric word for that is ball. So spheres are only shells. It's the points that are exactly that distance. If you want to talk about like a solid object that's full, that's a ball, and you can transform this into a ball by talking about everything with radius less than or equal to that, then you get a ball. We're going to deal with spheres and sphere-ish shapes, parts of spheres, a lot when we start doing triple integrals, especially in various different coordinate systems. So getting the sphere practice in early should be pretty helpful, I think. I don't think there's anything else that I need to say about this section. If there is, then you can encounter it on the homework and be confused and ask me some really good questions about it in class. I look forward to it. That's it for 13.2.